All right. So now we're going to move on to discussing two of the four common probability distributions associated with discrete and continuous random variables. And we're splitting them into two pairs, Poisson and uniform, which oftentimes deal with intervals of time, and then binomial and hypergeometric, whose main distinction is replacement. As they typically fall into pairs for this course, we're going to cover them by pairs to help distinguish the differences so that you can more easily tell the differences between the two. So we're going to start with the uniform distribution, and here we'll particularly focus on the continuous uniform distribution. So the idea behind the continuous uniform distribution is that, number one, every individual data value has the same chance of occurring as any other individual data value, as indicated by the word uniform, i.e. same chances. And then continuous means that instead of a bunch of discrete values, it is a range of values. A great example of this deals with time, such as in this example, flight times. You could have a flight, say, going from Houston to Albuquerque, and it might have a flight duration somewhere in the ballpark of 2 hours to 2 hours and 20 minutes. Now, typically when airlines talk about arrival times, it's usually in intervals of about 5 minutes. Unless you have ones like American that like to specify it down to the minute, but that's no more than guesswork. For the same reason why, if you were living off campus and driving to campus, you would not email your professor and say, "Professor, I'm going to be 5 minutes and 23 seconds late. Please make space for me." No one does that. Because no one says they're going to arrive in 5 minutes and 23 seconds. However, you could theoretically arrive in exactly 5 minutes and 23 seconds. Of course, you could also arrive in 5 minutes and 23 and 4/7 of a second, and so on and so forth. What that means is that the chances of any extraordinarily specific time to occur in this distribution would be 1 over infinity, because you have an infinite number of values, but the probabilities add up to 1. So therefore it would be 1 over infinity. So the chances of any given time occurring, an extraordinarily specific time, would be essentially 0. However, that doesn't mean it can't happen. Again, we use the lottery example. If we have an infinite number of options, and each of them has a chance of 1 out of infinity, then by expected value, one of them's got to happen. So that explains, again, the supposed paradox. Even though it's not really a paradox. So, let's now get to some properties of the continuous uniform distribution. The mean of our uniform distribution, continuous uniform, is going to be equal to the highest possibility plus the lowest possibility. Divide those by 2. You'll recognize this is the midpoint formula. So in this example, the lowest is 120, highest is 140, midpoint 130. That'll be the mean, or the expected time. Which makes sense. If they all have the same probability, half of them are below, half are above, the middle one's going to be the mean. The variance is equal to the difference between the high and the low. We square that and divide the whole thing by 12. You might say, okay, that numerator kind of sort of makes sense. Where the hell did this 12 come from? What 12? Where? Technically, it comes from calculus. This is not a calculus course, and generally speaking, we don't care about the variance of a uniform distribution all that much compared to other distributions. And the reason why is straightforward. You don't need the variance. You can just look. They all have the same chance. Just look at the length. Literally, by definition, the variance is dependent on the length, because the high minus the low is the length. So the length of the distribution pretty much strictly determines its variance. So you just look at it. The wider it is, the more variance. Nothing else to it. So now let's talk about actual probabilities associated with this uniform distribution. So let's suppose we ask, what's the chances of being in between two times? Say time A and time B, or data point A, data point B. That'll be equal to the difference between B and A divided by the length of the uniform distribution here. So the highest minus the lowest. Max minus min, you can do high minus low, max minus min, doesn't matter, same thing. So for example, if I asked you, what are the chances of your flight time being from 125 to 135 minutes, 135 minus 125 would be 10, and the length of distribution is 20 because 140 minus 120, so we'd have 10 over 20, 50%. You'd have a 50% chance of being in between 125 and 135 minutes. Straightforward enough. We do have a couple of shortcuts. They're very mild shortcuts. You can just use this base formula and still be fine. But the chances of being just below a certain data point or time is going to be equal to that data point minus the minimum over the max minus the minimum. Here's why. When we say x is less than b, we're really saying from a is less than x is less than b, where a is the minimum. So in this case, a is just the minimum. So if we had, say, less than or equal to 135, that'll be this divided by this. So 135 minus 120, so 120 is the min, divided by 140 minus 120, we'd have 15 over 20, 75%. And similar logic holds if we go the other way. So being above some cutoff time. If we're above 125, then our upper end is 140. So what we're subtracting our data point minimum from is going to be the maximum in both cases. They're very mild shortcuts. They're not the same level of wonderful shortcuts that you'll see with, say, hypergeometric, but nonetheless can be a little bit useful. Now, we do have some laws for continuous distributions. The chances of being greater than or equal to A and less than or equal to B is the same as being greater than A but less than or equal to B, which is the same as being greater than or equal to B, greater than or equal to A and less than B, which is the same as being greater than A and less than B. You might say, what part of this matters? This part is the one that matters. What this is saying is that whether or not you include the endpoints in your computation doesn't matter. And here's why. Let's go to our example up here. 125 to 135 minutes. That might as well be 125.00000, a bunch of zeros to the end of time, and then a 1 at the end, to 134.999999999, a bunch of 9s. Since any very super specific time has a chance of 1 out of infinity to occur, whether or not we include that one specific point doesn't matter. So whether or not we include the endpoints in the calculation doesn't matter. You might say, oh, then the formulas would change. No, they wouldn't. Because you might have, say, b minus a plus 0.0000001. Doesn't mean a thing. Doesn't mean a thing. So, as a practical matter, we usually use this one. Because it's a bit easier to write, a bit easier to understand. Really, this is just the math version of saying the chances of being in between A and B. That's all it means. Essentially, you'll notice a bit of a pattern here in this course. What I try to do is take what we say in English and put it in math form while still being correct. Or the other way around. Because part of what makes math and stats useful is if you can take what you found out and explain it to others. It can only mean so much if you give a technically correct explanation, but you confuse the ever-living bejesus out of whoever you're talking to. And for the shortcuts, same idea. So we're just going to stick with the less than, greater than symbols. If you want to include the equal sign, you can. Doesn't matter. So now that I've done that, here I have a practice problem. And actually, what we've talked about is enough for you to work on it. This one will be the uniform distribution because it says every time has an equal chance of occurring. So I want you to go ahead and take a moment to work on this practice problem, and then I will go over the answers. All right, let's start with part A. So it's asking us what the chances are of it being this, shall we call it, an extraordinarily specific time. Well, 15.0356373 seconds. Technically 0. Although, again, if you use it in minutes, it doesn't matter. So we're just going to put essentially 0. So for part A, it's going to be essentially 0. Any individual extraordinarily specific time has 1 out of infinity chances of occurring. And here, for whatever reason, that part confused you, I can switch it to minutes. Same idea. 1 out of infinity, 0. Basically, same idea. All right, let's now do part B. What are the odds of it being no longer than 18 minutes? So we're asking for the probability that our time is no longer than 18 minutes. So less than or equal to 18. In this case, this is the uniform distribution. And so this will be the uniform where our time, by our shortcut, we can just shorthand it to less than 18. This is going to be equal to 18 minus the lowest possibility, so 10, divided by our maximum, which is 20, minus our minimum, which is 10. And that comes out to 80%. So now part C, what are the odds of it being roughly 15 minutes? Which we will take to be 15 plus or minus 2 minutes. That is 13 to 17 minutes. Part C is an excellent example of taking how we speak in English and converting it to math. Or vice versa. If you're going to pick your parents up from the airport, let's say you're going to Lubbock, Preston Smith, you're going to pick them up. When you say, I'll be at the airport in about 15 minutes, you don't mean the stupidly specific time of 15.0356373 minutes. You don't call it around and say, hi, Mom, I'll be at the airport in 15.0356373 minutes. No one does that. When you say 15, you mean about 15 minutes. Sometimes you literally say, I'll be there in about 15 minutes. Otherwise, you say 15. But nobody understands that to mean literally 15 minutes on the nose. Usually, when we say 15, we mean something like, plus or minus 2. We don't say, Mom, I will be there in 15 plus or minus 2 minutes. We don't say that. We just say 15 minutes. This is taking that and converting it to math speak. So we're asking, what are the chances of it being somewhere from 13 to 17 minutes? And so that is equal to the uniform from 13 to 17, which is equal to our B, which is 17, minus our A, which is 13, divided by the high minus the low. In this case, that comes out to 40%. Now you might say, hold on a moment, it's more likely than not that I'm going to be wrong. Yep, welcome to life. When you're going to pick your parents up from the airport here, there's a pretty decent chance there might be a traffic jam, or you have a garbage stoplight. On the other hand, you might get extraordinarily lucky and get a ton of green lights. That's how the real world works. There's uncertainty. And you'll see with part E, when we quantify that variance, that just welcome to the real world. However, the thing is, 30% of the 60% that you would be wrong on is in the good end. You'd be early. Most people won't complain about you picking them up from the airport early. Unless you got there so quickly that, you know, they're nowhere close to being out there. But then you get to wait, not them. That's your problem. Anyways, let's now go on to part D. For part D, we want the mean. This is going to be equal to the high, which is 20, plus the low, which is 10. We divide that by 2. So here it'll be 15. Whether or not you include the label doesn't matter that much. Everybody understands the label to be what it is. If you're in, say, a chemistry class, oh yeah, the label matters a ton. Here, what else is it going to be? 15 bananas? That makes no sense. Hi, Mom, I'll be at the airport in 15 bananas. What the hell does that mean? So, generally speaking here, it's understood what the units are. We care more that you know what you're doing. Finally, part E. Let's calculate the variance. So here, I'm just going to put the variance of this uniform. We recall it is equal to the high minus the low. Square that. Divide the whole thing by 12. So that is going to be 20 minus 10. Square that and divide it by 12, which is about 8.333 minutes. If you square rooted that, so 8.333, and you took the square root of that, you'd get about 2.887 minutes. That variance, and therefore standard deviation, helps explain why this 15 plus or minus 2 is slightly more likely than not to not have the correct arrival. Again, welcome to the real world. All right. So now, we're going to move on to the Poisson distribution, but there's something I want to briefly review before we get to it, and that is the factorial. The factorial is denoted by the exclamation point. Whether or not you want to be excited about it doesn't matter. Who cares? Factorials are for integers. In this case, positive integers. Or you could say non-negative, doesn't matter. Now, you can find factorials for the real numbers. That's a graduate level study, and we're not really concerned about that. So here, the n factorial essentially means n times n minus 1. This is not algebra. This n, you know what the n is. It's not algebra. Times n minus 2, times n minus 3, so on and so forth, all the way down to times 3, times 2, times 1. Or we can put it in a notation called product notation. It looks like a fancy table, at least by handwriting standards. From n, or well, from 1 to n, of I. You might say, okay, I'm completely lost. Explain both of these to me, please. Let's do that. Let's start with the easier one, and then this one. This notation doesn't matter right now. It's going to matter for the next lecture. That's why I'm introducing it to you now, while I have an accompanying example for it to make sense. So here, an example. Let's suppose we had 9 factorial. That'll be equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is a large number. That is 362,880. That's how factorials work. You just multiply all the positive integers up to and including that number. To use this notational form, very formal notation, in this case, we would first have I equals 1, so that would be 1. Now, we increment it by 1. Because whether it's a sum notation or product notation, we always increment by integers of 1. So now I becomes 2. And then we increment it to 3. And we just keep going up until we hit n, which in this case is 9. So 4, 5, 6, 7, 8, and 9. The product notation just means whatever you have in here, you multiply them onto each other. So with summation notation, we had, say, the sums of products. With here, you might have the products of sums. It can be the other way around. And in fact, you'll see in the next lecture, you'll have the other way around, products of sums. For now, do not worry too much about the product notation. I'll review it again in the next lecture. It's the factorial one you have to be more careful of. Additionally, we have 0 factorial is equal to 1. You might say, why? How do we do this? Should it be 0? 0 times 0 is 0? No. A factorial means how many ways we can order something. If we have nothing, how many ways can you order nothing? Once, one way. You can order nothing in one way. Nothing. If you have one thing, how many ways can you order that one thing? Once. You might say, no, twice. We can order the one thing as nothing. No, you have to order the something somehow. Nothing can be something, and something can be nothing. But this is not a philosophy class. This is a math class, so we'll just accept that 0 factorial equals 1. There are many other ways of showing it. That's the conceptual way. So now that I've explained what the factorial is, let's come up to our second distribution, known as the Poisson distribution. The Poisson distribution, it's not the Poisson distribution. It is the Poisson distribution. It is named after a French guy. And we denote it by, I use the Greek letter rho. It looks like a P that fell down the stairs. Or maybe it's like an elderly P. Whatever. This is equal to the mean raised to the power of x, which is your cutoff or your input, times e to the power of the negative mean, which in this case is Euler's number. Euler's number is 2.712 blah, 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 blah. Now, the good news is, when you're using Desmos, which there's a video called the Desmos Assistance video, you should go over that and watch it. Watch the Desmos Assistance video. It will show you very exactly how to use these things. You can just straight up type in the letter E into Desmos, and it'll do this part for you. And I say, okay, fine, what is E? E is Euler's number. How do you spell Euler? Easy. E-U-L-E-R. You might say, hold on a moment. You got the first two letters completely screwed up. Well, you could probably guess the nationality of this guy. He's French as well. Apparently, the French are good at two things: naming things after themselves and losing to Germans. But hey, this is a math class. We name things after who discovered them. So E is Euler's number. And then in our denominator, we have x factorial. So there's that factorial popping up. Now you might say, I'm lost. Well, let's start with an easier part. For the Poisson distribution, the variance and the mean and the expected value are all the same. That's it. So the good news is, when it comes to variance and expected value, you don't have to compute it, just give it to you. And then, of course, standard deviation squared to the variance. So now regarding this formula, notice at the start of the problem we'll give you the mean. So you'll have this. You know what Euler's number is. That's 2.712 blah, 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 blah. You know what the mean is. You already have that. So all you're doing is having one input. Additionally, you can put this in a Desmos. So you can literally enter this in right in a Desmos, and it'll take it. Now, you'll have to replace the row with a P because there's no row on your keyboard, but you get the point. Again, please watch over the Desmos Assistance video. It will show you exactly how you do these things. So, now that I've talked about it, what is it for? The Poisson distribution is primarily used for use of intervals over time, so say number of arrivals over time, so on and so forth, where the probability of success over time does not change, and whether or not something occurs or does not occur is independent over time. A couple of examples of this, say number of planes arriving at a gate, or number of people going through a drive-through, number of people stopping by the pharmacy. Those are good examples of it. If you notice the pattern with Poisson and uniform, at least the continuous uniform, we use them with time a lot, and that's how it's easy to get things mixed up. Another thing is both of them, there's independence. The probabilities of success don't change. You might say, well, then what's the difference? They both look the same to me. With the Poisson distribution, you'll notice that the probabilities of any given numbers occurring are not the same. So the probability of having one arrival will not necessarily be the same as the probability of having 3 arrivals. Or the probability of having 5 arrivals will not necessarily be the same as having 6 arrivals. It's the uniform where all the probabilities are the same. So when it comes to comparing uniform Poisson, the key phrase you're looking for is equal chances of occurring, or not necessarily equal chances of occurring. If the things have equal chances of occurring, it's going to be uniform. If it's not necessarily the case, Poisson. At least we're dealing with time, for the most part. So here what I want to do is give an example. So here, I want you to do these 5 parts. C, D, and E should be very straightforward. A should be relatively straightforward. Part B, you might be a little bit confused. But the hint for part B is this. You can use the complement law. No, because remember, when we were talking about those laws in the previous lecture, they apply everywhere. They apply everywhere. So, I'll give you a moment, and then we'll go over the answers. So let's start with part C. What is the mean? The mean number of cars is 5. That is a reading question. What is the variance? The variance is equal to the mean. So, 5. The standard deviation is equal to the square root of the variance. So that's the square root of 5. That's it. C, D, and E are that easy. Let's now do A and B. Let's start off by constructing our distribution. So we have the mean raised to the power of x. So we'll have 5 to the power of x. Then we have Euler's number, so 2.71, to the power of the negative mean. So e to the power of negative 5, not positive 5, negative 5. And then we divide it by x factorial. That e, you know what e is. That's not a variable. E is not a variable. It's not really an input either. It's just a number. Now here's what you do. Again, I go look at that Desmos Assistance video to show exactly how to input it. But here, you just take this, enter that straight into Desmos. You enter it correctly. It'll say, cool, now give me an input. So in this case, we want the probability of exactly 4 cars. So the probability of 4 cars will be equal to 5 to the power of 4 times e to the negative 5 over 4 factorial. And this comes out to be roughly 0.175. So there's a 17.5% chance that for this drive-up teller for the bank, we'll get exactly 4 cars. over that window. Now let's do part B. We cannot do row of 1. In fact, row of 1 is going to be an answer choice, and it's not going to get full credit because it's asking at least 1 car. So we want the probability of getting at least 1 car. This is equal to 1 minus the probability of getting no cars. So this is equal to 1 minus the chances of no cars occurring. So now, again, you can put this straight into Desmos and it'll spit out a number for you, assuming you've already entered this. It'll do that for you. And you'll be allowed to use Desmos on the test, at least for my sections with Professor Bailey. Hopefully other instructors will as well, or at least give you some comparable calculator. Again, though, if you have me, Professor Bailey, then I will let you use Desmos. So here we have 1 minus row of 0. That's 5 to the power of 0 times e to the negative 5 over 0 factorial. You technically don't need a full calculator to get an exact answer here. 5 to the power of 0 is just 1. 0 factorial is 1. So these two cancel out. You're left with 1 minus e to the negative 5, which comes out to approximately 0.993. So there's a 99.3% chance at least one person is going to drive up this window over this 50-minute period. That is to the extent to which the difficulty of Poisson comes. If I had asked you for the chances of no more than 1, then it would be row of 0 plus row of 1. But at least if you're in my section with Professor Bailey, then there is a practice test for this unit, and it gives you some ways to practice even more with these. So now that I've talked about these two distributions, what I want to do is give you a practice problem where you first identify whether it is Poisson or uniform, and then you start working things out. When dealing, that's not how you spell. So when dealing with Poisson uniform distributions, you're primarily looking to see whether or not the outcomes have equal chances of occurring. So key words or phrases. Same chance of occurring. Another one you could look at is equal probabilities. And then a third one could be uniformly distributed. So now you have that. I'm going to give you a practice one. I want you to identify whether it's the Poisson uniform distribution and then explain why that's the case. I then want you to compute the mean and then do a computation associated with it. Again, if you're in my sections on the test, it'll be structured almost exactly like this. I'll ask you to differentiate between two scenarios for Poisson uniform, and then one of them I'll have you do a computation or two associated with them. So I'll give you a moment, and then we'll go over the answers. All right. Poisson or uniform? This will be the uniform distribution, because any flight time has the same chance of occurring as any other flight time. Means all times are uniformly distributed. So now what's the mean? Well, the mean, since it's uniform, it'll be the high minus the, the high plus the low, divided by 2. So 35 minutes. Now let's suppose you're one of those people that says, screw you airlines, I'm going to schedule my layover to be 10 minutes after this flight lands because you are a risky person. Maybe this is where Part C can help you. In fact, most airlines, when you do a layover, they'll give you at least a 45-minute buffer to guarantee you can get your flight. However, you don't technically have to do that. You can schedule them separately and be risky, but then you can't blame the airlines for it. So maybe something like this can help you figure out whether or not you want to do that. So here, Part C is asking us, what are the chances of it being longer than 36 minutes? So we're asking the chances that our flight is longer than 36 minutes. This is equal to the uniform distribution of our flight being longer than 36 minutes, which will be equal to the high, or the max, minus our input of 36, divided by the high minus the low. So that'll be equal to 40%. That's it. Nothing else to it. The hardest part of Poisson and uniform are the conceptual parts, not the actual math. Now when we get to binomial and hypergeometric, it'll be the exact opposite. It'll be figuring out which is each is easy, but doing the computations gets annoying. If you want more practice with this, there's more practice with it both in the WebWorks and in the practice test. So now, let's return to our normal distribution, because a normal distribution can sometimes refer to times. Of course, normal distribution can refer to most things, so we're going to talk about a bit of the normal distribution now, and then talk about a bit of it again in the next lecture. So here, the z-scores, they don't have to come out as integers, and the data points don't even have to be integers themselves. So the z-score formula is still the same. This part, all that I'm saying is let's now compute z-scores that are not necessarily integers. So I want you to do parts A, B, C, D, E, and F and get your answers for these. The only new part is your answers, your final answer, might not be an integer. But z-scores don't have to be integers. We started off introducing them as integers, so it was easy to understand what was happening. Now, let's expand it to all the realm of possibilities. That's all we're doing here. Otherwise, the formula is the same, so I'll give you a moment. Go ahead and work on this. All right, so here we have a mean of 85 and a standard deviation of 17. So with all of these, it'll be xi minus 85. I'm sorry, not Lord, where the hell did I get 17 from? 7. There we go. Sorry about that. So we have our input minus 85 divided by 7. Let's start with part A. In this case, we'll have 61 minus 85, which is negative 24. Divide that by 7, so we'll have negative 3.429. Let's now do part C. 74.5 minus 85, negative 10.5. Divide that by 7, negative 1.5. Part E, 95.5 minus 85 is a 10.5. Divide that by 7. This one is positive 1.5. Going back to part B, 68 minus 85 is 17. Divide that by 7, negative 2.429. Part D, 85 minus 85 is 0. Divide by 7, still 0. And then 99, we have 99 minus 85, 14. Divide that by 7 is 2. Some of these are integers, some weren't. Some of the ones that weren't integers were nice decimals, others were not. That's how z-scores work. Otherwise, now that I've shown they can be decimals, we've been working forwards. Time to work backwards! This would be a system of two equations. What I'm going to do is I'm going to work out this first part, this first question, and then I want you to do the second one. Now, if you want to just go and challenge yourself and try doing this now, you can. But I want to point out on the lecture notes, I worked out the most arbitrary case possible to get you a generalized formula. If you want to use that, you're more than welcome to. You don't have to. Choose whichever is best for you. So I want to show you how we work these out. So we have an x value of 2 corresponding to a z-score of -1. So -1 is equal to our x value, which is 2, minus the mean, which we don't know, divided by the standard deviation, which we also don't know. Our next one, we have an x value of 11, a z-score of 2, corresponding to an x value of 11. So that'll be 11 minus the mean, which we don't know, divided by our standard deviation, which we don't know. You might say, where are these equations coming from? That's just this. We're plugging in the z and the xi. Since we have 2 equations and 2 unknowns, we can solve the system of 2 equations to solve for each. So what we're going to do, we're going to multiply out the denominator. So we have -1 times standard deviation is equal to 2 minus the mean. And then here, 2 times the standard deviation is equal to 11 minus the mean. So now, I'm going to subtract 2 from both sides. The negative standard deviation, minus 2, is equal to the negative mean. Over here, we're going to have 2 times the standard deviation, minus 11, is also equal to the negative mean. Now that we've equated them, we now have just one equation. So we have the negative standard deviation, minus 2, is equal to 2 times standard deviation, minus 11. So, add 11 to both sides. So, -2 plus 11 is 9. Add the standard deviation to both sides, clear that one out. That's going to be 3 standard deviations. So, 9 is equal to 3 standard deviations away from the mean. So, our standard deviation is equal to 3. Plug that back in up here. 2 times our standard deviation of 3 is equal to 11 minus the mean. So, add the mean to both sides, subtract the product, and so the mean is going to be equal to 5. So therefore, our mean and standard deviation are 5 and 3. Now this problem has an extra step. On the actual test and on the practice one, I'm not going to give you the extra step. So here, you'd be done for all intents and purposes. At least for the first part. But I'm going to do an extra step. I'm asking what z-score corresponds to an x value of 5. Easy. The z-score is equal to our x value of 5 minus our mean of 5 over 3. So 0. Here, the key part, as long as you know how to set up the system of 2 equations and then you multiply out the standard deviations, it's just very elementary high school algebra 1. So then, in that case, I want you to do this practice one. This is going to be the difficulty level of it for the test, so I'm going to give you a moment to work on it. All right, let's go over the answers. So we have a z-score of -1.4. That corresponds to having an x value of 3 minus the mean, which we don't know, divided by the standard deviation. Our other one, we have a z-score of -0.2, and this is equal to an x value of 9 minus the mean over the standard deviation. Multiply the standard deviations out. We have -1.4 times the standard deviation. That looks like a 6. Is equal to 3 minus the mean. And -0.2 times the standard deviation is equal to 9 minus the mean. So we're going to subtract 3 and then subtract 9 from both sides. So we have -1.4 times standard deviation minus 3 is equal to the negative mean. And then over here, we have -0.2 times the standard deviation minus 9 is equal to the negative mean. So therefore, negative 1.4 times the standard deviation minus 3 is equal to negative 0.2 times standard deviation minus 9. In this case, we're going to add 1.4 of the standard deviation to both sides. We're going to add 9 to both sides. Negative 3 plus 9 is 6. And negative 0.2 plus 1.4 is 1.2. So therefore, the standard deviation is equal to 5. Now, let's plug that back in. I'm going to plug it in up here. Let me draw a better arrow. So we have negative 0.2 times 5 is equal to 9 minus the mean. Add the mean to both sides. Add this product to both sides. The mean is equal to 9 plus 0.2 times 5. So the mean is equal to 10. And these two correspond to our answers. So therefore, the mean and the standard deviation are 10 and 5. On the test, what it might do is flip it. It might have an answer choice of the standard deviation is 10 and the mean is 5. You do that, you're only getting half credit because you didn't read. What the test also will do is give you answer choices corresponding to accidentally having these flipped. You might accidentally flip those and say 3 is equal to negative 1.4 minus the mean over the standard deviation. If you do that, you're going to reach the wrong answer. Otherwise, when it comes to normal distribution and z-scores, this is the z-score part. So we've now covered the remainder of the conceptual parts associated with these z-scores. In the next lecture, after we talk about binomial and hypergeometric, then we'll start dealing with the other part of it, probabilities associated with a normal distribution. Otherwise, that's all for the third part of the 4 through 6 lecture series. Hope you all have a great rest of your day, and I'll see you next Tuesday.